Okay, so we said that we'd like to do limits with a little bit more methodically. In other words, back here we tried to do this limit here. We tried to do this limit, kind of just analyzing it, or I'm sorry, this limit as x goes to 3 from above or 3 from below. We just sort of looked at the top piece and we looked at the bottom. We tried to think about it, but we'd like to come up with something which would allow us to do things with a little bit more methodically, and these laws will help us. So we're not going to prove these laws, but maybe we'll just sort of think about them. So they say, suppose that c is a constant and that these limits exist. So we're saying that we have a function f and we have another function g, so we're going to be dealing with two functions, not just one. And we're saying that if we talk about the limit as x goes to a for f, that exists. Remember, we said sometimes limits exist and sometimes they don't. So we're going to assume that this exists. Maybe we could call it L or L1. We're also going to assume that this limit exists. Same a, but a different function g. I could write x in here, or I don't have to. And let's call this one L2 maybe. Remember, this means that we have some function f, for example, and at a, the limit exists. Whatever, I don't know what the picture looks like, but we're just saying that the limit exists. And the same thing if we have a function g there, maybe of course, a different shape. So maybe it looks like that or something. Anyway, the limit at a also exists for g. Now, I happened to make these intersect there. I didn't mean to do that. Let me try and undo that and say it looks like this. So anyway, the limit at a for f exists, and for g it also exists. We're just assuming that these limits exist. Okay, so the first thing is that then we can say that the limit of f plus g, and we have a way of calculating it. So let's just take an example. This is a little bit abstract if we don't have examples. Let's just suppose that f is equal to x squared, for example, and g is some other function, let's say equals x to the eighth, for example. Okay, so what we're saying is, suppose we want to do the limit of f plus g for some reason. So in other words, suppose we're asking, I'm just leaving out some stuff here because it takes a long time to write it. Suppose we're asking, what's the limit of, we want to know the limit of x squared plus x to the eighth. So what this property here says we can do is we can break up this question into the limit of x squared plus the limit of x to the eighth. So that's all this property says. So I should fill this stuff in. I should say like as x, and let's say a specific a. Let's not just be so abstract just to say some unspecified a. Let's say a is actually equal to 2. So then the limit as x goes to 2 of this, we can do it like this. Now, we can do it like this means you don't have to do it like this, but you have the option of doing it like this. So if this turns out to be easier than this, you can do it this way. That's the idea. Okay, so what we're saying is whenever you have the sum of two functions and you want the limit of that, you can break it up into the limit of the first one plus the limit of the second. That's what this says. Whenever you have the sum and you want the limit of that sum, you can if you want. You don't have to, but you have the option of breaking it up into this separately and this separately and then add. Okay? And the same thing goes whenever you have a function minus another function, then you can break it up into the limit of the first one minus the limit of the second one. So if this had been minus x squared minus x3a, you could write this as the limit of x squared minus this one. So it's just the option. It doesn't mean you have to do it that way, but it allows you, this rule here and this rule here says that you can break it up like that. Okay, the third rule says that if you have something like this, suppose you want to know the limit of 5x squared as x goes to 3, for example. Suppose you want to know that. So this rule number 3, says that if you have a constant times a function, well, we do have a constant times a function here. So the constant is c, and I'm sorry, the constant in this case is 5. We call it in general c up here. So this rule says that if you have a constant times a function, you have, again, the option to rewrite this problem. Maybe you can make it easier by rewriting it like this. What are we saying? You can take the constant, which is, we can say, inside the limit sign, right? We're doing the limit of this whole thing. So this constant is part of the limit question. But what it says is you can take it out. So you can sort of make the limit question a little bit easier and just multiply the result by c, by the constant. So in this case, it means you can take 5 out and write the limit of just x squared. So you're allowed to take this 5 out, and that seems to make the problem easier, because multiplying is not very hard, but doing limits of complicated stuff is going to be hard. So why not reduce the complicated part by bringing the 5 out, and then you have a kind of easier limit problem. So I have to write this part as x goes to 3. Okay, so this rule says that you can do that. You can take if you have a constant times a function, you can take the constant out. Okay, so this might make doing a limit problem easier. And then we have this one. So let's suppose we had a question like this. Suppose we had x cubed times the sine of x. And we wanted to know the limit of this as x goes to something, 5. Okay. So this looks pretty complicated to do. And this next rule, rule number 4, gives us a way to break it up maybe into easier pieces. So what does it tell us? We say this is one function times another function. So we could call this function f and this function g. So if this rule says if you have one function times another, and you're asking for the limit of that product, which is what we have here. We have a f function, x cubed, and a g function, sine of x, and we want the limit of its product. We can rewrite it. Maybe it will make it simpler. Maybe it won't, but maybe it will. Limit of x cubed separately, as x goes to 5, times the limit of the sine of x as x goes to 5. Okay, so we can rewrite this problem as this one times this one. You don't have to do that, but this might turn out to be easier to do than this, and you're allowed to rewrite it according to this rule. Now, we haven't proved any of these rules. We're just throwing them at you and saying these are all okay to do. The reason we haven't proved them is because we really haven't defined really carefully what limit means. I mean, we have a basic idea of what it means, but we don't have a hard and fast, rigorous mathematical definition of it. We haven't presented that. So without that, we can't really prove these, and we're not going to cover that, the rigorous one, in this course. So anyway, so we're just throwing these at you and saying you're allowed to do this. So what are you allowed to do? If you have one function times another and you want the limit of that whole thing, you are allowed to break it up into the limit of the first piece times the limit of the second piece. And maybe that will make it easier. If it doesn't make it easier, you don't have to do it that way. But this gives you the option of doing that. And finally, the last rule there is that if you have something like this, for example, suppose you wanted to do sine of x over x cubed as x goes to something, let's say, again, let's just say 5. So what does it say you can do? If you have one thing divided by another, you're allowed to split it into the limit of the top one and the limit of the bottom one. So, as I said again, it may make it easier. If it does, you're allowed to do this. If it doesn't, you don't have to do this. Limit of the bottom piece. Okay, so these are examples of how we can use these rules. Now, of course, or I don't know if I should say of course, but if the bottom limit turns out to be 0, then you're not really allowed to do this, because when you get 0 on the bottom, you get some kind of problem anyway. So this rule only applies if the bottom limit does not turn out to be 0. Okay, so if we want to express these in words, so like this one, if we want to express that in words, it says that the limit of a sum is equal to the sum of the limits. So it says the limit of a sum is equal to the sum of the limits. The limit of a sum is equal to the sum of the limits. This one would say the limit of a difference is equal to the difference of the limits. And this one would say the limit of a constant times a function is equal to the constant times the limit of the function. So this one is, they often express this as saying you can take the c, sorry about that, do that again. You can take the c outside the limit sign. So in other words, you can make the limit part of the problem a little bit simpler and just multiply by the c at the end, like this. Okay, and this one says the limit of a product is the product of the limits. The limit of a product is the product of the limits. And this one says the limit of a quotient is the quotient of the limits, as long as the bottom limit is not equal to 0, provided the denominator is not equal to 0. Okay, so we can express them like that.